Somewhere in a government facility in the Nevada desert, engineers once stood behind thick concrete walls and watched a nuclear reactor scream to life, its exhaust glowing white-hot, hydrogen gas exploding out of a nozzle at temperatures that could melt steel in seconds. This was not science fiction. This happened in real life, more than 50 years ago, and the engine they built was powerful enough to cut a trip to Mars down to a fraction of the time it takes today. Then the program was shut down, the blueprints were shelved, and for half a century humanity kept sending astronauts into space using rockets that are, in essence, controlled chemical explosions, the same basic technology that carried Apollo astronauts to the moon. But right now, in laboratories and test facilities across the United States, that old shelved technology is being pulled back out, redesigned and rebuilt. Because if human beings are ever going to walk on Mars and come home again in one piece, chemical rockets alone may not be enough. This is the story of nuclear propulsion, the technology that could take the most dangerous journey in human history and cut it down to a fraction of its current length, and the story of why, after all these decades, we are finally serious about using it. Let's start with the problem. Because to understand why nuclear propulsion matters, you first have to understand just how brutal a trip to Mars actually is using the rockets we have today. Mars is not next door. Even at its closest approach to Earth, it sits somewhere around 54 million kilometers away, and that closest approach only happens once every 26 months, when the orbits of Earth and Mars line up in a way that makes the trip efficient. Spacecraft do not fly to Mars in a straight line. They follow a curved path called a home and transfer orbit, which is the most fuel-efficient way to get from one orbit to another, but it is not the fastest. Using this method, a crewed mission to Mars would spend somewhere between 7 and 9 months just getting there, another several months to a year or more waiting on the Martian surface for the planets to realign for a return trip, and then another 7 to 9 months getting home. All in, we are talking about a mission that could last 2 to 3 years, with astronauts spending the vast majority of that time confined to a spacecraft roughly the size of a small apartment. That length of time is not just an inconvenience. It is arguably the single greatest obstacle standing between humanity and Mars. Every additional month in deep space multiplies the risks. Galactic cosmic rays, which are high-energy particles that stream in from beyond our solar system, do not care about spacecraft hulls. Unlike the radiation from solar flares, which can at least be somewhat shielded against with mass and water, galactic cosmic rays are made up of particles moving at close to the speed of light, and they punch through aluminum, punch through plastic, and can even punch through several feet of water shielding. The longer astronauts are exposed, the higher their lifetime cancer risk climbs, the more damage accumulates in their central nervous system, and the greater the chance of long-term cardiovascular problems. NASA's own studies have shown that current radiation exposure limits could be pushed to their absolute edge, or beyond, on a mission using today's chemical propulsion timelines. Then there is the muscle and bone loss that comes from months of microgravity. The psychological toll of isolation and confinement in a tin, can millions of kilometers from home, the risk of equipment failure with no chance of rescue, and the sheer amount of food, water, and supplies that have to be carried along for a multi-year journey. Every one of these risks scales with time. Cut the transit time in half, and you do not just make the trip more comfortable, you fundamentally change the risk profile of the entire mission. This is where nuclear propulsion enters the conversation, and it is worth pausing here to clear up a common misconception, because when people hear the word nuclear next to the word rocket, their minds often jump straight to explosions or meltdowns in space. That is not what we are talking about. Nuclear propulsion for space travel is not about building a bomb that pushes a spacecraft forward, at least not in the systems being seriously developed today. It is about using the incredible energy density of nuclear fission, the same basic physics that powers nuclear submarines and power plants here on Earth, to heat propellant to extreme temperatures far beyond what chemical combustion can achieve, and then expelling that propellant out of a nozzle to generate thrust. The math behind why this matters is actually fairly intuitive once you break it down, so let's do that. Rocket engineers measure engine efficiency using a number called specific impulse, which is essentially a measure of how much thrust you get out of a given amount of propellant, and it directly correlates with how fast a rocket can ultimately travel. The best chemical rocket engines humanity has ever built, engines burning liquid hydrogen and liquid oxygen, top out at a specific impulse of around 450 seconds. That is genuinely impressive engineering, refined over 70 years of rocketry, and it is very close to the theoretical maximum for chemical combustion. A nuclear thermal rocket, by contrast, can achieve a specific impulse of 800 to 900 seconds, roughly double that of the best chemical engines, using the exact same propellant, liquid hydrogen. That doubling in efficiency does not just mean a modest improvement. It means a spacecraft can carry less fuel for the same mission, or the same fuel can produce dramatically more velocity change, which translates directly into faster transit times, more payload capacity, or both. To understand how a nuclear thermal rocket actually works, picture a compact nuclear reactor, not unlike the ones used to power naval vessels, but built specifically for the extreme demands of spaceflight. Liquid hydrogen, stored in a cryogenic tank at temperatures hundreds of degrees below zero, is pumped through channels running directly through the reactor core. As it flows through, the hydrogen absorbs the intense heat generated by the ongoing nuclear fission reaction inside the core, heating up to temperatures around 2,500 degrees Celsius in a matter of milliseconds. This superheated hydrogen gas then expands rapidly and is forced through a nozzle, exactly like a traditional rocket engine, generating thrust as it exits. The fundamental difference is the heat source. A chemical rocket generates heat by burning fuel and oxidizer together in a combustion chamber, a process limited by the chemical energy stored in those molecular bonds. A nuclear thermal rocket generates heat through nuclear fission, splitting uranium atoms inside a reactor core, a process that releases an amount of energy per unit of mass that is literally millions of times greater than any chemical reaction. That is the entire secret behind the performance gain, and it is why nuclear thermal propulsion has been the subject of serious engineering attention since the very earliest days of the space age. The history of this technology is genuinely remarkable, and most people have never heard of it, which is part of why so many viewers find this topic fascinating. In 1955, years before Apollo ever put a human being on the moon, the United States began a program called Project Rover, a joint effort between the Atomic Energy Commission and what would eventually become NASA. The goal was straightforward on paper and monumentally difficult in practice: build a working nuclear rocket engine. Engineers at Los Alamos National Laboratory and later at a specialized test facility in Jackass Flats, Nevada, began designing a series of experimental reactors under a program called Kiwi, named after the flightless bird. A fitting joke, since these early reactors were never meant to fly, only to prove the underlying physics and engineering worked on the ground. Between 1959 and 1964, engineers built and tested a series of Kiwi reactors, working through problems that ranged from managing incredible thermal stress on reactor materials to controlling the flow of superheated hydrogen without the entire system tearing itself apart. Some early tests ended in dramatic failures, including one infamous test in 1965, part of a related safety experiment called Kiwi TNT, where a reactor was deliberately driven into a destructive power excursion to study what would happen in a worst-case accident scenario, giving engineers crucial data on reactor safety. By the mid-1960s, this research had evolved into a program called NERVA, standing for Nuclear Engine for Rocket Vehicle Application, a collaboration between NASA, the Atomic Energy Commission, and aerospace contractors including Aerojet and Westinghouse. NERVA was not just a research exercise. It was intended to become an actual flight-ready engine, potentially powering upper stages for missions to Mars and beyond. Over the course of the program, engineers tested increasingly powerful reactor designs, including the Phoebus series, which at its peak generated over 4,000 megawatts of thermal power, and the NERVA XE Prime engine, which was tested in a configuration designed to closely mimic actual flight conditions, including firing the engine multiple times and testing it in a simulated near-vacuum environment. By 1968, the NRX-A6 reactor ran for over an hour at full power without any degradation, a genuine engineering triumph that proved nuclear thermal propulsion was not just theoretically possible, but practically achievable with the technology of that era. NASA's own internal planning documents from the late 1960s included serious proposals for crewed Mars missions using NERVA-derived engines, with some plans targeting launch windows in the early 1980s. And then, despite all of that progress, the program was canceled. In 1972, facing a shrinking NASA budget in the aftermath of the Apollo program, a shift in national priorities toward the space shuttle, and no immediately approved Mars mission to justify the expense, NERVA was terminated. It is worth being honest here about what really killed the program, because it was not a technical failure. It was not a safety disaster. It was budget politics and a lack of a defined mission that needed the capability at that specific moment. The engineers had built, tested, and largely proven a working nuclear rocket engine, and then the funding simply evaporated. For the better part of the next 5 decades, nuclear thermal propulsion research continued in fits and starts, mostly through small-scale studies and paper designs, but nothing approaching the scale of Project Rover and NERVA. That silence is finally coming to an end. Before we get to the modern revival, it is worth mentioning a completely different and even more radical nuclear propulsion concept that was seriously studied around the same era, because it illustrates just how far outside the box engineers were willing to think during the early space age. This was Project Orion, conceived in the late 1950s by physicist Freeman Dyson and others. Instead of using a controlled fission reactor to heat propellant, Project Orion proposed detonating a series of small nuclear explosive devices behind a spacecraft, with the resulting blast wave pushing against a massive shock, absorbing pusher plate to propel the vehicle forward. On paper, the performance was staggering, with some designs theoretically capable of reaching Mars in a matter of weeks rather than months, and even reaching nearby star systems within a human lifetime using larger-scale versions. In practice, the concept ran into an obstacle that had nothing to do with engineering: the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear explosions in outer space, effectively ending any realistic path toward testing or deploying Orion-style propulsion. Project Orion remains an important part of nuclear propulsion history, and it is a useful contrast to remember, because it shows that not every nuclear propulsion concept involves detonating bombs. The mainstream approaches being developed today, nuclear thermal and nuclear electric propulsion, use controlled, continuous fission reactions, not explosive devices, and that distinction matters enormously for both safety and international law. That brings us to nuclear electric propulsion, the second major branch of nuclear space propulsion technology, and one that works on an entirely different principle than the thermal rockets we discussed earlier. In a nuclear electric system, a fission reactor does not directly heat propellant. Instead, it generates electricity, which then powers electric propulsion thrusters, such as ion engines or Hall effect thrusters. These electric thrusters work by ionizing a propellant, commonly xenon gas, and using electric or magnetic fields to accelerate those charged particles to extremely high velocities before expelling them. The specific impulse achievable with electric propulsion is remarkable, often exceeding 2,000 seconds, several times better than even nuclear thermal propulsion. The trade-off is thrust. Electric thrusters produce very small amounts of thrust compared to thermal rockets, often measured in fractions of a newton, meaning a nuclear electric spacecraft does not blast off toward Mars the way a nuclear thermal or chemical rocket does. Instead, it accelerates gradually and continuously over weeks or months, slowly building up velocity through a long, gentle burn, following a spiral trajectory rather than a quick, powerful push. This makes nuclear electric propulsion particularly well suited for cargo missions, where transit time is less critical than efficiency, since a nuclear electric tug could ferry heavy equipment, habitats, or supplies to Mars ahead of a crewed mission, using a fraction of the propellant a chemical system would require. Some proposed architectures for future Mars missions actually combine both approaches, using nuclear electric propulsion to preposition cargo and infrastructure on an efficient, patient trajectory, while reserving nuclear thermal propulsion, with its much higher thrust, for the crewed vehicle that needs to make the trip as quickly and safely as possible. This hybrid approach appears frequently in recent NASA mission architecture studies, and it represents a genuinely elegant way of combining the strengths of each technology while minimizing their respective weaknesses. Now let's talk about what is actually happening right now, because this is not purely a history lesson. Nuclear propulsion is having a real resurgence, and the reason is a renewed, serious national commitment to sending humans to Mars. The most prominent modern program is called DRACO, an acronym for Demonstration Rocket for Agile Cislunar Operations, a joint effort between DARPA, the Defense Advanced Research Projects Agency, and NASA. Announced in 2023, the DRACO program awarded a contract to Lockheed Martin to design, build, and fly an actual nuclear thermal rocket engine in space, marking the first attempt to test this technology in orbit since the cancellation of NERVA half a century earlier. The reactor itself is being developed by BWXT Advanced Technologies, a company with deep experience building naval nuclear reactors, and it is designed to use a special type of nuclear fuel called high-assay, low-enriched uranium, often abbreviated HALEU, which offers a reasonable balance between reactor performance and the non-proliferation concerns that come with handling nuclear materials. The DRACO demonstration mission has faced schedule adjustments, as complex aerospace nuclear programs often do, with the flight test now generally targeted for the latter part of this decade. But the underlying engineering work continues at a serious pace, and it represents the most advanced practical nuclear propulsion hardware development since the Nixon administration. NASA has run parallel efforts as well, through its Space Nuclear Propulsion Project, working alongside contractors to mature nuclear thermal propulsion technology for eventual use in crewed Mars architecture studies. These efforts build directly on the metallurgical and reactor design lessons learned from NERVA, but with the benefit of 5 decades of advances in materials science, computer modeling, and manufacturing techniques that simply did not exist in the 1960s. Modern reactor cores can be simulated and stress-tested computationally before a single physical prototype is built, dramatically reducing the cost and risk associated with the iterative testing that consumed so much of the original program's budget. The United States is not the only nation pursuing this technology. Russia's space agency, Roscosmos, has for years discussed a concept called the Transport and Energy Module, sometimes referred to by the acronym TEM, envisioned as a nuclear electric-powered spacecraft capable of serving as a space tug for cargo and eventually crewed missions throughout the solar system. Progress on this program has been difficult to verify independently given limited public disclosure, and it has faced its own share of delays and funding uncertainty. But it reflects that Russia has also identified nuclear propulsion as a strategically important capability for deep space missions. China has likewise expressed interest in nuclear propulsion as part of its own long-term deep space exploration ambitions, including stated goals around nuclear-powered spacecraft for missions to Mars in the 2030s. It is worth being clear and honest here, because a responsible science channel should always separate what is confirmed from what is aspirational. Several of these international programs remain in relatively early conceptual or developmental stages, with limited independently verified technical details available publicly. Unlike the DRACO program, which has documented contracts, named contractors, and specific technical milestones that have been publicly reported. So what would an actual Mars mission using nuclear thermal propulsion look like? And how much time would it really save? Based on published NASA and industry mission architecture studies, a nuclear thermal propulsion system could potentially reduce the one-way transit time to Mars from the current 7 to 9 months down to somewhere in the range of 3 to 4 months, depending on the specific mission design, the mass of the spacecraft, and how much of the available performance advantage is used to increase speed versus increase payload capacity. Cutting the transit time roughly in half is not a marginal improvement. It fundamentally changes the entire risk equation of a Mars mission. Having the transit time roughly halves the cumulative radiation exposure from galactic cosmic rays during the journey. It roughly halves the physiological toll of extended microgravity exposure on astronaut muscle and bone density. It dramatically reduces the amount of consumables, food, water, and life support resources that need to be carried along, which in turn allows for a smaller, lighter, and less complex spacecraft, or alternatively allows more of that saved mass budget to be reallocated toward additional safety systems, scientific equipment, or contingency supplies. It also meaningfully shrinks the total mission timeline, which reduces the cumulative probability of an equipment failure occurring somewhere along the way, simply because there is less total time during which something could go wrong. Faster transit time also opens up more frequent launch opportunities, because nuclear thermal propulsion provides significantly more velocity change capability than chemical propulsion for the same amount of propellant mass. Mission planners gain more flexibility in choosing launch windows, rather than being restricted entirely to the narrow 26-month home and transfer windows that current chemical propulsion architecture essentially demands. This added flexibility could prove critical for a sustained, repeatable program of Mars exploration, rather than one-off missions separated by years of preparation. Of course, none of this comes without serious engineering challenges, and it would be dishonest to present nuclear propulsion as a simple, solved problem waiting to be deployed. Let's talk honestly about the obstacles that remain. The first major challenge is materials science. A nuclear thermal rocket reactor core has to withstand extreme temperatures, intense neutron radiation, and the corrosive effects of superheated hydrogen flowing directly through its structure, all while maintaining precise structural tolerances, because any deformation in the reactor core geometry could catastrophically affect performance or safety. During the original NERVA program, engineers struggled significantly with fuel element cracking and erosion caused by exactly these conditions. And while modern materials science has produced far more durable ceramic and composite fuel matrix materials, since then, this remains one of the central engineering challenges of the entire field. The second major challenge is radiation shielding, and this is where a lot of public misconception tends to concentrate, so it deserves careful explanation. A nuclear thermal rocket reactor, while operating, does produce significant radiation, primarily neutrons and gamma rays. Engineers address this challenge in several ways. First, distance itself is an extremely effective shield, since radiation intensity drops off rapidly the further you get from the source, which is why reactor engines are positioned at the aft end of a spacecraft, as far as practically possible from the crew compartment. Second, a shadow shield, a relatively compact, dense shielding structure placed directly between the reactor and the crew compartment, can block the direct line of sight radiation path without needing to encase the entire reactor in shielding material, which would add prohibitive amounts of mass. Third, the liquid hydrogen propellant itself, stored in large tanks that are often positioned between the reactor and the crew area, provides meaningful additional shielding, since hydrogen-rich materials are actually quite effective at absorbing neutron radiation. It is also critical to understand that the reactor is not operating and produces essentially no meaningful radiation until it is safely away from Earth and its crew, typically not activated until the spacecraft has reached a sufficiently high, stable orbit, specifically to minimize any risk associated with a potential launch failure. This has been a core safety requirement in every serious nuclear propulsion program designed since the 1960s, and it directly addresses the most common public safety concern: the fear of a launch failure spreading radioactive material in Earth's atmosphere. The third challenge is testing. This might sound like a mundane bureaucratic issue, but it is genuinely one of the most difficult practical obstacles facing the field. During the original NERVA program, engineers could test reactor engines relatively openly in the Nevada desert, running them at full power and studying their exhaust plume directly, because environmental and nuclear safety regulations of that era were far less stringent than they are today. Under current environmental and nuclear regulatory frameworks, ground testing a nuclear thermal rocket engine at full power, with its exhaust containing some radioactive particles from the reactor core, is enormously more complicated, requiring specialized containment systems to capture and filter the reactor exhaust before it can be released, a capability that essentially has to be built from scratch. This is one of the significant engineering and regulatory challenges that programs like DRACO have had to work through, and it is part of why timelines for these programs have shifted over the past several years, reflecting the genuine complexity of validating this technology safely under modern standards, rather than any fundamental doubt about the physics involved. The fourth challenge is nuclear non-proliferation policy. Because nuclear thermal propulsion reactors use enriched uranium fuel, any program developing this technology has to carefully navigate international non-proliferation frameworks and agreements, which is precisely why the choice of high-assay, low-enriched uranium fuel for the DRACO program was such a significant decision. This fuel type offers meaningfully better reactor performance than the low-enriched uranium used in most conventional civilian power reactors, while still remaining below the enrichment threshold that would raise the most serious proliferation concerns associated with weapons-grade material. Navigating this balance between performance and policy has been, and will likely continue to be, a defining feature of how nuclear space propulsion programs are designed and regulated going forward. Let's also address the psychological and public perception dimension of this topic honestly, because it matters enormously for how these programs move forward. Surveys of public attitudes toward nuclear technology consistently show a level of anxiety that is often disproportionate to the actual statistical risk involved, largely shaped by a small number of highly publicized nuclear accidents on Earth, incidents that involved completely different reactor designs, operating in completely different contexts than the small, purpose-built, carefully shielded reactors being designed for spaceflight. Space agencies and their partners have to work not just on the engineering, but on transparent public communication, clearly explaining the safety architecture built into these systems, the fact that the reactor remains inactive until safely in orbit, and the decades of accumulated experience the nuclear industry has in reactor safety engineering. This is a genuinely important part of the story, because ultimately, Public and political support determines whether ambitious, expensive, long-term programs like this receive the sustained funding they need to actually reach flight readiness, which is, after all, exactly what happened to NERVA in 1972. So where does this leave us, looking forward from today? The DRACO program's in-space demonstration flight, whenever it ultimately occurs, will represent the first time in over 50 years that a nuclear thermal rocket engine actually operates beyond Earth's atmosphere. And it will provide the flight heritage data that is essential before any agency would commit to using this technology for an actual crewed mission. If that demonstration succeeds, the next logical steps would involve scaling the technology up to the size and power levels required for an actual Mars transit vehicle, integrating it with a habitat module capable of supporting a crew for several months, and conducting further uncrewed test flights to build confidence in the system's reliability before ever putting human lives aboard. Realistic mission architecture studies published by NASA in recent years have generally discussed crewed Mars missions using nuclear thermal propulsion becoming feasible sometime in the 2030s, contingent on sustained funding, successful completion of the DRACO demonstration and follow-on testing, and continued political commitment to a genuine Mars exploration program, none of which are guaranteed, but all of which appear more plausible today than they have at any point since the Apollo era. What makes this story genuinely compelling is not just the engineering, it is the sense of unfinished business running through it. In the 1960s, American engineers built and successfully tested a working nuclear rocket engine, an achievement that could have fundamentally changed the timeline of human deep space exploration, and then watched that capability get shelved for budgetary and political reasons that had nothing to do with whether the technology actually worked. 5 decades later, facing the same fundamental problem, the brutal, dangerous length of a Mars transit using chemical propulsion, we are picking that thread back up with better materials, better computational tools, and a renewed national ambition to actually put boots on Martian soil. Whether nuclear propulsion ultimately becomes the technology that carries the first human Mars mission remains to be seen, and there are real, serious engineering, regulatory, and funding challenges still standing between where we are today and that goal. But the physics has not changed since 1968, when the NRX-A6 reactor ran for over an hour at full power in the Nevada desert. Nuclear fission still holds an energy density that chemical combustion simply cannot match, and that fundamental advantage, first proven with real hardware over half a century ago, may finally be about to send human beings to Mars in half the time it would otherwise take, and bring them home again. If you found this exploration of nuclear propulsion technology valuable, consider subscribing for more deep dives into the science and engineering shaping humanity's future in space. And let me know in the comments which topic in space exploration you would like to see covered next.